Let's finish all this up by looking at how hearing works and also balance, or equilibrium, static and dynamic equilibrium. So in the same way that light was an electromagnetic wave, sound is a mechanical wave. It's a disturbance of air molecules. So when something makes a sound, that disturbed the air. So the air has rarefaction and compression, and it does that in a wave-like sequence, and that hits your tympanic membrane, and that's how hearing takes place. So just like the electromagnetic waves, sound waves can be characterized by their pitch, which is the frequency, the wavelength, and the amplitude or the loudness. Now, whereas with light, we look mostly at the wavelength, not the frequency. With sound, it's going to be the opposite. We're going to look at the frequency rather than the wavelength. Amplitude as well. So, frequency, pitch, the higher frequencies have higher pitches, all right? So, which wave represents the lowest note? 1, 2, 3, or 4? So remember, frequency is the key here. How many wave forms are there within that specific amount of time? And yeah, that would be the lowest of all the notes, all right? Which would be the highest note? That would be the one on the bottom. It has the highest frequency. See? That's all there is to it. And then amplitude, all right? Amplitude is the size of the wavelength, all right? That corresponds to the loudness. It's the height of the wavelength, I should say. So there you go. Higher amplitude waves are louder. So notice both of those sounds have the same frequency, the same pitch, all right? They both have 3 wavelengths within that same period of time. But the bottom one has a much higher amplitude, therefore it would be a much louder sound, okay? So what's going to happen here? I'll kind of trace this through. So you see out there at the pinna, the sound hits your pinna, your auricle, goes down the auditory canal. Look what happens. The middle ear amplifies the sound. So the malleus, incus, and stapes, the mechanical conduction there, the vibration of the bones, actually amplifies the sound so that you can hear better. Bone conduction. Inner ear then transforms air waves into fluid waves, all right? That's what's going to happen when the stapes goes into the oval window. We now have, remember, the paralymph and the endolymph, the fluids in there. We're going to make a wave. The air waves are now being transduced into fluid waves. Inner ear also transduces physical energy into action potential, so that's what's actually going to happen in the spiral organ. We're going to turn the physical energy into nerve energy. So, physiology of hearing. Sound waves cause tympanic membrane to vibrate, okay? That's amplified then the malleus, the incus, the stapes, fluid waves, and the paralymph, the scala vestibuli. They cause the basilar membrane to vibrate, which causes the stereocilia, the fancy name for the hair cells, in the spiral organ to pivot against the tectorial membrane, all right? And that causes action potentials in the cochlear branch of cranial nerve 8. So what happens here is that when you look in the upper illustration there, see, they've uncoiled the cochlea for us. So now we're seeing it at its base out to its tip. So high frequency sounds cause the basilar membrane to vibrate more near the base, all right, which is narrow and stiff. So again, the sound is going to cause, as it moves through the scala tympani, it's going to cause the basilar membrane to vibrate. But different frequencies will cause different wavelengths in the fluid, and that will cause the basilar membrane to vibrate most at different portions. So high frequency sounds cause it to vibrate most near the base, whereas low frequency sounds cause it to vibrate most out near the apex, where it's wide and flexible. So that's all it comes down to. The different frequencies just have to do with how much or where on the basilar membrane it vibrates, and the amplitude is basically how much vibration takes place, all right? So that's all we need to know about sound. It's basically just the spiral organ there transducing the physical energy, transforming it into nerve energy. How does human hearing compare to animals? We're actually pretty good. You can see where that, whatever that would be, fuchsia? I don't know. So we hear lower sounds than a lot of animals do. There are a lot of animals that can hear higher than we do. But generally speaking, we're pretty good in the animal kingdom. All of our senses actually are pretty darn good. We're not the best at anything, but overall, we're pretty good at everything. We have good vision, good smell, good hearing, good taste. Well, some of us have good taste, others don't. Note the scale here is logarithmic, so it's a little exaggerated compared to the linear scale, but yeah, overall, we're pretty good. So, static equilibrium, linear movement, all right. Otoliths are crystals of calcium carbonate. The word otolith, oto, ear, lith, stone. So otoliths, crystals of calcium carbonate, literally ear stones, embedded in a jelly-like otolith membrane. So there you see in the upper right, and on the lower right as well. Otoliths embedded in that jelly-like membrane. And so for static equilibrium, linear acceleration in the position of the head. So in other words, moving in a straight line, and also how you tilt your head. That's what gets detected here. So we have macular receptors in the utricle and the saccule, and they have these little hair cells. Tilting the head causes the otoliths to deflect the hairs, all right? And that causes then potentials, right? Direction of the tilt indicates the direction of the movement. So the utricle responds best to horizontal movement, saccule responds best to vertical movement. And that's what it comes down to. It's just the deflection of these hair cells creating potentials that then your brain can figure out and go, whoa, we're leaning to the left. See, that kind of a deal. Action potential is carried by the vestibular branch of cranial nerve 8. Oh, I talked over the cranial nerve 8. That's what I was saying. So dynamic equilibrium, this is rotational motion. So crista are located in the ampulla of the semicircular canal. So remember, in that wide part down at the base of the semicircular canal, the ampulla, there are these crista receptors, all right? And there's endolymph inside, and there's a little cupula. And rotational motion causes the cupula to bend in the opposite direction. So you see there the ice skater twirling, the cupula will bend in the opposite direction of the rotation. Once again, hair cells will change the rate of impulse generation, and the vestibular branch of cranial nerve 8 will carry that information to the brain. And there you go. There's rotation right there. It's not even moving, but it looks like it, doesn't it? That's all there is to it. There's much more. Hearing and balance, equilibrium, are much more complex than this. But for a 200 level class here, that's all we need to know. You can actually take whole classes just on auditory perception, and they're really interesting too. So there's a lot more to it than what we've covered. We just covered the very, very basics. Okay, which statement is false? Proprioceptors provide information about body position. Anosmia is the inability to smell. The lens is anterior to the iris. Tears contain antibodies and enzymes. Opioids cause constriction of the pupils. 4 of those are true. 1 of them is wrong. Which one is wrong? Yeah, the lens is posterior to the iris. It's behind the iris. And we've officially reached the end. That's all. That's all, folks. So we've made it. We got through all of Bio 201. So study hard. And Bio 202 will be next.